Today I'm very glad to tell you a little bit about the Milky Way Bulge and Milky Way Bar. So let's start. Okay. So this is the Milky Way Bulge seen in near infrared. Okay, and the top image is a COBE image. So COBE was launched in 1990s. Can you see my marking? Yeah. Okay.
Yes. Yes.
So.
Yeah. Yeah, it's okay.
Yeah. So and the bottom image is a WISE image. That's the more latest near infrared satellite. And I just want to emphasize that if you look at the Milky Way in the near infrared, and the dust extinction effect is minimized, and you can see that previously if you see everything in optical bands, then you don't see much because the dust will obscure your line of sight. And in the central region of the Milky Way, you can see that there's this parallel, it's like a box, but also looks asymmetric, asymmetric, non-symmetric. Okay, something wrong with my tongue today, and on the left side you see that the bulge seems to be a little bit bigger than the other side, and we will explain that. And this is due to the aspect effect of our viewing our line of sight to the bar major axis. And the stars in most stars in the bulge appear to be quite old. There can be even much older than the 5 gig years. Okay. And these stars cover a wide range of metallicity gradients, so they from metal rich to metal poor, so this is also a very interesting aspect of the Milky Way bulge. And so how do we understand the nature of the Milky Way bulge? We live in the Milky Way, and we are located on the Milky Way disk. So that's an advantage. So it's an advantage to study every single star in the Milky Way bulge, but it's also a huge disadvantage to see to understand the nature of the Milky Way bulge, because we are in it. We are at a disadvantageous position to see it. And in Chinese, we have an ancient poem saying, if you are in a mountain, you cannot actually see the whole the whole mountain. I'm sure there's a Persian verb as well. So this is exactly the same situation we have in the Milky Way. So suppose if we don't have mirrors and we want to see how we look, and what do we do? So we look at our surroundings, right? We look at other people. If my brother has 2 eyes, then I probably have 2 eyes. If my brother has 1 nose, I probably also has a nose. So I think it's a very good perspective. Can be obtained by studying the external bulges. Okay, and but the definition of the bulge of a bulge is also not easy. To the first order, you can imagine that this is surface brightness, and that's radius, and so to the first order, this galaxy is essentially an exponential disk showing in this straight line, and a central concentration. Okay, that's the bulge part. So just from this 1D decomposition, you roughly know that this galaxy is essentially a bulge plus a disk, right? And because the halo of this galaxy normally is very faint, and dark matter halo is invisible. So this is the first order approximation, right? But exactly how do we define a bulge? You can say that the bulge is this roundish thing sitting in the middle, of a disk. That's from photon. So that's not very helpful actually. And if you want to quantify things, and you can do it, you can categorize its morphology through photometry. And for face-on galaxies, and we think that we define the bulge as the extra light in the center. And for edge-on galaxies, we identify the bulge as the brighter and thicker center, as shown in the right figure. Or you can define a bulge through the kinematic of stars. And so in this figure, the y-axis is maximum rotational velocity divided by velocity dispersion. It's basically a ratio of rotation, regular rotation, to the random motion of stars. And the x-axis is the flattening of a bulge, or elliptical galaxy. And you can see that, so this is so-called Binet diagram. Basically, this figure tells us that if the galaxies are, or the bulges are in this region, then it's not very much flattened by rotation. Its flattening is acquired through the random motion, non-equal or a non-isotropic random motion in different directions. And so this galaxy, if it's close to that line, this is called oblate line. If oblate isotropic rotators. So if a bulge is close to that line, and then we say that the bulge is mainly rotation dominated, and this bottom blob, that's more like random motion dominated. So all these definitions are surrogate definitions. So they're relatively easy, but you don't really know what they are physically. And a better way to define bulge is through the physical definition. And that way that we basically define things through the physical processes. Okay, and so there's the so-called classical bulge. And the classical bulge is, in our mind, we imagine that the classical bulges are mini ellipticals. They tend to be made in mergers or merging clumps. And the Circic index tends to be bigger. And the Circic index equal to 1, this is exponential. I'm not sure if everybody familiar with the terminology. And for Circic index equal to 4, then a galaxy follows R2 1/4 law. This is also the Duvall-Coulers law. Okay, so and the exponential is a defining characteristic of these galaxies, and the n equal to 4 is more closer to the traditional elliptical profile, density profile of elliptic galaxies. And for classical bulges, they normally they are not rotation dominated, but they do have rotation. And it's very important to realize that classical bulges and the elliptical galaxies, they both sit on a fundamental plane. Okay, so it's basically a plane defined by the size of the galaxy, the velocity dispersion or temperature of the galaxy, and the surface brightness of the galaxy, which is the density essentially. So this fundamental plane relation was first defined by ellipticals, but we do find that some classical bulges also sits on the fundamental plane. And the other type is so-called pseudobulges, and the pseudobulges are basically formed from the disk by internal cellular processes, and often driven by a bar. And so once material are driven towards the center by the bar, and they often form young stars, and they still have some residual gas and dust. And since the stars come from the disk, so they still have their memory of the disk origin, so they are more rotation dominated, okay, as opposed to the dispersion dominated in the classical bulge case. And the therapeutic index is slow. It's closer to exponential disk. And so to depends who you ask, and this may also include a category called boxy bulges. Okay, and I tend to think boxy bulges are separate class from these two. So this is a more like a physical definition. So we understand the physical path clear, but the classification is more difficult. Okay, so so we have a dilemma here. So no, what? And talking about the boxy bulges, so the boxy bulge is also very common in edge-on disks or in disk galaxies. But once we can only detect them clearly when they are sort of edge-on. Okay, and these are some examples. You know, this is a like boxy bulge, and this is boxy bulge also like a peanut-shaped bulge, and same thing here. And this one is also very clear, and you can almost see a X-shaped structure in the middle. Okay, so so this guy did the statistics on edge-on disks, and he concluded that about 45% of the disks have peanut-shaped bulges. Okay, so just to remind you that this is actually quite comparable to the fraction of strong bars. So, you know, hinting a possible connection between the boxy peanut-shaped bulge and barred galaxies. Okay, so right now I think it's relatively well established that our Milky Way is uh, it's roughly the bulge. Milky Way bulge is roughly the Milky Way bar seen edge on. Okay, and we have hints of Milky Way bar since a few tens of years ago, and so the bars do exist, or we know that it exists for quite some time, and this was first hinted by the non-circular motion of gas. So if you have a bar, you don't expect the gas to stay on circular orbits, and this non-circular motion, the gas was a major uh, evidence for Milky Way for the existence of the bar. Also, you can study the bulge through stellar photometry, and basically star counts, and so star counts distribution is asymmetric. Um, so we now think that the bulge is probably the bar seen nearly end on. So this angle, the angle between the sun GC line and the bar major axis, this angle is about 20-30 degrees. Okay, and this is our Kobe image. And the top, the face on is only an artistic impression. Okay, it's beautiful, but it's not real. And it's just an impression based on scientific data. So this our current understanding basically builds up in the recent from the recent surveys and dynamical modelings. Just to name a few, this Brava survey and Argos survey. There are more radial velocity surveys, and the more recently GIBS survey, VVB survey, and Gaia ESO survey. So I think before I talk about the modeling of the Milky Way bulge, I just want to say that um, there are commonly two approaches to study to model the bulge formation, and one is through the full-fledged hydrodynamical models in cosmological simulations. And these hydro simulations generally are very complicated because the subgrid physics is quite uncertain, and they are also very expensive. So you may get some appealing results, but it's very hard to separate out the physics involved because everything is all together. Okay, and also there's another simpler approach, which is the approach I have taken. Um, so that I like to start building simpler model. So you have fewer free parameters to tweak, and it's easier to explore the parameter space more extensively. And so this way, the main advantage is that you can isolate out the important physical effects in play and understand what effect is caused by which physical process. And this helps you because they're simple, so you can run many of them. And this helps the to do quantitative comparison with observations. So I think the latter approach is the approach I have taken, and I think simple models are still very useful. They can be a very good starting point. You understand them, you understand the physics in these models, and then you gradually add in more complicated processes step by step. And so this way we gradually unravel how nature works. And so basically the two approaches are complementary. Okay, I'll come back to this. So we have found that a very simple model can match the survey data very well in many aspects. And the right movie. Can you see the movie? Is it moving?
Yes,
Okay,
yes, it's okay.
I assume it's working. Also, this model starts from a thing called disk, then a bar forms in the horizontal direction, and look in the vertical direction. Vertical direction, then you see that the disk after bar forms, it becomes forms a wave-like instability, and that instability is called buckling instability. So, not only that we understand, we see that. The simple model can match the survey data well. We also understand the physical mechanism behind this evolution, and it's basically a result of two instabilities happening back to back. So the first instability is the bar forming instability in plane, and after the bar forms, then you have a second instability in the vertical direction. I'll talk about the buckling instability in the next slide. And after the vertical instability saturates, then you're left with a thickened boxy bulge. Okay, and we think that we argue that this boxy bulge is just the edge on view bar. Uh, so the bottom this the bottom line is that it's the bulge is made in an instability of a precursor disk instead of previous major mergers, as most people believe for classical bulge formation. Okay, and so I mentioned the buckling instability, and now we know that the buckling instability criteria is basically the if the vertical random motion is much less than it's less than the random motion in a plane, and then the whole disk suffers from this buckling instability. So this instability is very related to the firehose instability in plasma physics, where if you have a hanging garden hose and you put a strong flow of water through it, and this garden hose will begin to oscillate. So, and it's also very similar to the Kelvin-Helmholtz instability. If you have two fluids of float at each other, and if they have horizontal motions, then you tend to form this kind of instability. And similar instability possibly explains why there are so few ellipticals more elongated than E6 or E7. So E7 is very elongated elliptical. And this also hints at the maximum disk axial ratio is around 3 to 2. And another way to think of this is you can think of um, the, the the vertical natural frequency, the kappa z. If it's too low, and then the the disturbances tends to have a higher frequency than the natural frequency, and so the disturbances tends to be damped, just like in a forcing oscillator case. Okay, and so this is a surface brightness map uh, through this simple model. So after the bar formed and the boxy bulge formed, so this is a 3D view. And if our sun is here, then you look through here and here, you see that, sorry. And so on this side, you see the near end of the bar. So everything is brighter and bigger. And this side, you see the fainter end of the bar. And because they're far away, so they are dimmer and they look smaller. And this is exactly what we see. So on the positive longitude, you see a bigger, um, this side, the left side is bigger than the right side. Okay, and it's qualitatively similar to what the Kobe satellite tells us. Okay, and the other dynamical property of the bar, like bar angle, and pattern speed, axial ratio, bar length, etc., they're roughly consistent with other independent studies. Okay, and more important, not only we get a good match in photometry, we also can match the stellar kinematics very well. And so this is the early result of Brava. And keep in mind this is already 10 years old. And so in the Brava survey, basically the survey is mapping the Milky Way bulge in using stellar kinematics. So every circle here contains about 100 stars, and then you measure its radial velocity, line of sight velocity. Then you can measure its mean velocity in that field and the velocity dispersion. This is exactly what we're showing here. And the first column is along this direction, b equal to -4, and that's mean velocity. This is the velocity dispersion, and as a function of galactic longitude, which is this direction. Okay, and you see that the second column is this direction, and the third column is along the L equals 0 minor axis, and you see the model match the observation very well and almost go through all data points at the same time. And this is not a fit. Okay, the model wants to do anything it wants, so it's not a direct fit. It looks like a direct fit, but it's not. Okay, and one thing you can see that important characteristic of the Milky Way bulge is that it displays very strong cylindrical rotation, which basically means the rotation is relatively constant regardless of this height. So if you away from the central midplane, and the rotation profile is very similar. So this one is roughly quite similar. So this is so-called cylindrical rotation, and this aspect is especially hard to match with a classical bulge. Okay, and in this process, in this bar forming process, we also naturally get a peanut-shaped bulge. Okay, and this peanut-shaped bulge was first predicted to by a buccal bar since the 90s, and so it's good that we can now see they actually match the Milky Way bar as well. So once after the bar buckles and after the buckling instability saturates, you're left with a central peanut and outer thin part. Okay, and so if the movie stops, anyway, movie keeps running, but you see what I meant. So the central peanut and outer thin part. And actually, in the Milky Way, we also found there's possibly a long thin bar uh, outside of this bulge bar. So, this kind of boxy shaped, peanut shaped bulges is also seen in external galaxies. And this is a boxy bulge, just like our Milky Way. So they are very common, and they're very common seen in external galaxies. Another consequence of the peanut is that if you observe the Milky Way bulge through the sun, and this is the Milky Way bulge, our cartoon shape of Milky Way bulge, okay, and then you study the bulge fields, and by measuring the distance distribution or apparent magnitude distribution of some tracers, some tracer population. And here we use, people generally, I didn't use it. So the observers tends to use red clumps because they are bright and as a standard candle to measure distance. Okay. And if you plot out the apparent magnitude distribution, and you tend to see the apparent magnitude distribution tends to display two peaks. So this is a bimodal distribution. And this is exactly because at the sun's location, if you look through this peanut, and you will see two clumps in your line of sight. Okay. And so in the past, people call it X-shaped structure, and people still call it X-shaped structures, but we think it's basically it's a reflection of the central peanut. They're not really X-shaped like a letter X shape. At least I don't think it's that extreme. And so basically, the existence of the X-shaped bulge is another evidence that the Milky Way bulge formation is shaped mainly by internal dynamical instabilities and not the bulge, not instead of the mergers as people commonly assume. Okay, and we can also predict um, the, the kinematics of this X-shaped or peanut-shaped bulge. And so we make model predictions for the on the kinematic property of the bulge and X shape, and they seems to be quite reasonable. So this is the top is the model, and the bottom is some observation. They are not very different. So this is line of sight velocity, and that's velocity dispersion. And pay attention, the velocity dispersion seems to be elongated in the vertical direction. We don't know completely know why, and the observations also show very similar structure. So it will be further cross-checked by a large upcoming surveys like Gaia. And as a matter of fact, there's recent papers like Clark et al. 2019. They have already cross-checked using the VVV proper motions. And it's very interesting that once you have good data, it's also possible to determine the distance to the galactic center by using the star's spatial distributions. So the star's spatial distribution tends to be in a peanut or X-shaped structure, and if you identify the arms, and so the central region, the cross region, gives you the distance to the galactic center. Okay, let me check the time. Be with you. Okay, like 30 minutes. Okay, I still have 15 minutes, so I
Yeah,
need to go a little bit
you have enough
faster.
time. You have
Yeah.
enough. Thanks.
Huh?
I said you have enough time.
Yeah.
I
Okay.
about 10 minutes.
Well, it's okay. I think I have 15 minutes or something. Okay, and the recent VVV survey and Gaia proper motions also shows that the fainter and brighter red clumps, they seems to have different proper motions. Okay, and so this is showing in this kind of clumps, and they do have very different proper motions. Because previously, some people have questioned using red clump as a good standard candle. They say that maybe red clumps are not good standard candle, and this is just showing you that overall the red clump stars can be used as a good standard candle to trace the X-shaped structure or peanut-shaped structure. So I think this is a very strong evidence against the interpretation that there are two type of two population of red clumps due to multiple populations. So if that explanation is correct, then they are located in the same distance, and the proper motion will appear to be similar, but which is not the case. Okay, and so I probably skip this. So this is some orbital studies when we study the Milky Way bar, and we think that we can find another way to classify orbits, and that's based on angular momentum, and in angular momentum space. So I'll probably skip this. So this is basically we find that in the angular momentum space, the as we know that in a rotating frame, the angular momentum of stars is not really conserved. The only conserved quantity is the Jacobi constant or Jacobi integral. That's like a energy in the rotating frame. Although LZ is not conserved, we may use the average value divided by its dispersion to 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 this could be served as a very good proxy of the second integral motion. So we know the second integral motion exists, but we don't have the its analytical expression. So we think that this proxy may be very useful, and so I'm going to skip this part. If you have more questions, feel free to ask. Okay, a bar's signature can also be seen in the shape, the detailed shape of a line-of-sight velocity dispersion profile. So if this is the Milky Way and this is the Milky Way bar, and the bar is not exactly aligned with our line of sight, if the bar is around this direction, and you look at one line of sight direction, the other line of sight direction, you see that the velocity distribution, line of sight velocity distribution, it's not a Gaussian, and it has skewness, and we found that there's a very good correlation between the skewness of the distribution and the mean velocity of this distribution. So this is the similar correlation are also seen in external peanut-shaped bulges. So it's an indication, possible indication of various end on bar. So this is very consistent. Okay, and we also find that such simple bar models can also explain the gas features in the Milky Way. So the gas features in the Milky Way. So in general, if you have gas in a spiral galaxy, and we say that the gas is driven towards the center, but they are by the bar, but they're not directly to the very central region. Okay, instead, they often form this very nice looking ring and so-called circumnuclear ring or nuclear ring. Uh, and so the physical, and we, in our recent studies, we think that we understand the physical mechanism better. And you, for first of all, you need to have enough resolution in your gas simulations. If you don't, then you tend to form smaller but wrong nuclear rings. So we extended this gas bar-driven gas inflow studies to the Milky Way. Previously, it was on the generic bars, and we found that uh, 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 the best fitting bar plus spiral models can reproduce most gas features in the observed LV diagram. So many people probably not familiar with the LV diagram. So the LV diagram basically is because we don't have very good distance measurements up to the gas clouds in our Milky Way. So instead, what people do is they plot out the line of sight velocity, which can be measured very accurately through Doppler shift, and the galactic longitude. And you can see in such figures, you can have the gas features here and there, and that's so-called the tangent point due to the spiral arms. And I can show you quickly how we how is our fitting results. And so basically we use base potential. That's the modeling result of the VV red clump giants. And so all we're doing is we use this as to constrain the galactic bulge density. And so once we have this base potential, then we can change we can add the spiral arms to this both base potential, then also vary the bar pattern rotation speed. This is bar pattern rotation speed we found, and also the spirals are also rotating, and we can also vary the spiral rotating speed. So the top is the face-on view are simulation results, and you see that the bar is somewhere here, and under the influence of the bar, the gas will be driven towards the center and often form a nuclear ring in the central region. And the same modeling results is displayed in the LV diagram. So this is the LV diagram. All the symbols and black points are from observations. As you can tell, that our simulated LV diagram match the observations reasonably well. And this is the circumnuclear ring, or molecular central molecular zone, and which is matched reasonably well. And we also try to paint different features with a different color, so you can have a one-to-one correlation in the face-on morphology and LV diagrams. Okay, if you're interested, you can read this paper. So not only we get a good match in the gas dynamical models, we also try to see if we can understand which feature is responsible to which physical feature is responsible for the creation of observed features. For example, we found that in order to reproduce the central molecular zone, or in other words, it's a Milky Way's nuclear ring, you need to add a central nuclear bulge. And this nuclear bulge is like the nuclear disk in our Milky Way. And so the point is that you need a higher central concentration in order to produce such a central molecular zone. And also we found that the bar quadruple moment or the long bar part, they are responsible for the creation of near and far 3 kpc arms in this region. Okay. and the spiral arms, if you change the spiral arms and rotation curves, then you change the tangent point, like here, the tangent point here, and the connecting arms and the vertical structures, basically. So we think we roughly know which physical feature is responsible for which observational feature. And there is also a very important observational constraint on the Milky Way bulge, which is vertical metallicity gradient. It basically means there are more metal poor stars at increasing height above the midplane. So this is the observation, okay? And so that's metallicity as a function of uh, um, galactic latitude. Okay, this is B is increasing, and so basically the galactic midplane is here. Okay, B equals 0 is here. As you go away from the midplane, you see that there's more and more this trend, more and more metal poor stars. So previously it was people used this gradient to argue against the scenario where bar is the bulge is the result of buckled bar. Why? Because people think that if you have a vertical gradient and after this violent buckling in the vertical direction, and this gradient tends to be erased. Okay, and we found that um, this gradient can still be generated after the violent buckling. So this is the modeling results. You see that it's not very far from observation. And so this is, and this mechanism is purely dynamical. And the trick is you need to set up an initial radial gradient in order to explain vertical gradient. And so the radial gradient is converted to a vertical one. I'll explain a little bit. The reason is,
We have almost 5 minutes.
oh, okay. So the reason is that different regions of the bar and disk is heated vertically differently. Okay, and so this is just to show um, once we saw initial radial gradient, and this radial gradient also predicted by inside-out formation scenario, and it's consistent with high disk observations, and you tend to form a stable metallicity distribution function after the buckling. Okay, and so I'm going to skip this. And so I just want to emphasize that this is a pure dynamical mechanism to set up to establish a vertical metallicity gradient. And before initially you have a radial metallicity gradient, and the disk is very thin. And after the bar formation, then the outer more metal poor stars shown in this blue curve, so they move inward, and they got heated the most in bar formation. And then after the buckling, this horizontal radial velocity dispersion is converted into the vertical velocity dispersion shown in dashed lines. Okay, so we basically find that the gradient is established in a two-step process. And compared with other scenarios, so this has less parameters to fine tune. And although if you have more than one disk, then you can improve the match. Okay, so we think that this is a basic mechanism that must be in action in other more advanced models. Okay, and so if you have a simple, as long as you have a simple star disk with a radial gradient, then this buckled bar, you will end up with a buccal bar with a vertical gradient. Okay. And of course, you need to compare these models, better understand the differences. Okay, and I'm going to skip this. This is just showing you that probably there's not a very significant classical bulge in the Milky Way. So if you have a much smaller classical bulge, it tends to have very high central surface brightness, and that's often much denser than star cluster and or disk exuded bulge, and we don't see that. And this is probably why. So the fact that we can detect a nuclear star cluster in the Milky Way shows that Milky Way contains almost no classical bulge. And this is Milky Way compared to other two external galaxies, and they look very similar. So it's and this galaxies, their bulge are also made of the very old and alpha enhanced stars. So it's not rare that the formation of the bar that now lives, the formation of stars that now live in bars finished quickly and early. So the basically the formation of stars in bulge and the assembly time of the bulge structure, they can be different. Okay, and the Milky Way probably also hosts an inner ring like some other external galaxies. So this is our gas simulation, and if we incline the simulation to nearly agile, and you see very similar structures as in other observed galaxies. Okay, so I'm going to quickly summarize, and basically I try to tell you that a very simple disk instability models, which is very simple, and with have fewer parameters to tweak, and the physical mechanism in this bar model is very well understood. And despite its simplicity, it ties together several isolated results in a coherent picture, and cemented by a fully evolutionary n-body model in which the bar evolves naturally and without much fine-tuning. So it can match the morphology of the Milky Way bulge, and also match the kinematics very nicely. And also we can get a photometric bar angle, bar length, bar pattern speed. They are all similar to other independent studies. I think it also very importantly, so that you can naturally form a boxy peanut shaped bulge, and this can explain the recent observations, and also quantitatively match the gas features in the Milky Way. And because our Milky Way doesn't have a classical bulge, this helps explain the fact that the Milky Way supermassive black hole is a little bit undermassive relative to the M sigma relation. Okay, we think that it's a really good starting point to this model is really a good starting point, and you can gradually incorporate more complexity in the future. So more details are can be found in this book. This is a review I wrote for a Springer book chapter. So this is a summary with some take-home messages. So Milky Way bulge may just be the Milky Way bar seen somewhat end-on, and its dynamics can be well matched by simple buckled bar models in which the bar evolves naturally and without much fine-tuning. As match can give it a good quantitative match to kinematics, also photometry, and also X-shaped structure, and possibly also the vertical metallicity gradient, which I didn't have time to explain all the details. So, and the Milky Way gas kinematics may also be well matched by a bar and spiral model. So overall, in some sense, it's a pseudo bulge, or it's not a classical bulge, made by mergers. It's a boxy bulge or pseudo bulge made by internal dynamical instabilities. And we think the physical processes are relatively well understood. And so in the last 10 years, we have witnessed a paradigm shift. So Milky Way bulges probably not made in mergers. Okay, I'm going to stop here. Thank you very much.